Welcome to our explainer. Today, we're diving into a really fascinating paradox hidden right at the heart of modern analytical chemistry. Just imagine a universally used scientific model that is, technically speaking, considered obsolete. It actually relies on physical structures that don't even exist in the real world. Yet, without it, laboratories everywhere would literally struggle to analyze complex chemical mixtures. We're talking about the theoretical plate model in chromatography. Let's unpack how a complete theoretical illusion helps scientists decode physical reality.
Here's our roadmap for today. We'll start with the illusion of movement, then look at the anatomy of a plate, the math of migration, simulating the separation, thermodynamics and equilibria, and finally, the legacy of an obsolete model.
Okay, let's jump right into part one, the illusion of movement.
So, how do we conceptualize movement here? Real-world chromatography is a completely continuous, chaotic fluid flow, right? And that makes it incredibly difficult to analyze mathematically. But our source material uses this brilliant analogy to solve the problem. It compares the model to a cartoon or a stop-motion film. Think about it. Just as a film is made up of individual static photographs that create the illusion of smooth motion when you play them back quickly, this mathematical model takes that continuous flow of chemicals through a column and breaks it down into a sequence of distinct, separate steps.
Taking that analogy a step further gives us our actual definition. The theoretical plate model is essentially a static, step-by-step mathematical approach. It takes that chaotic, continuous chemical flow and freezes it into digestible, discrete frames. And in every single one of these frames, the entire column reaches a state of new equilibrium before we ever move on to the very next frame.
Moving on to part two, anatomy of a plate. Let's zoom in a little closer to see what actually happens inside one of these theoretical frames, or plates as a substance, which we call an analyte, progresses through the column. In this model, an analyte experiences two entirely distinct states during its total migration time. First up, you have the time spent in the mobile phase, where the analyte travels at the exact same speed as the fluid. And second, there's the time spent in the stationary phase, where the analyte is completely immobile. So it's a totally binary experience. You're either moving at full speed, or you are completely stopped.
Now, within two successive transfers between moving and stopping, the concentrations re-equilibrate, and at each new equilibrium, the analyte has progressed by a tiny, distinct distance. We call this specific distance a theoretical plate. Because this is a static model, we take the entire physical length of the chromatography column, let's call that L, and we partition it into n number of theoretical plates. And the key here is that all of these plates have the exact same height, which we can calculate simply by taking L and dividing it by n.
Now you might be wondering, if this plate doesn't actually exist in the physical hardware of a modern liquid chromatography, why on earth do we use the word plate? Well, it actually comes from an older plate theory for distillation, described by the scientists Martin and Singh. The term stuck and is kept purely for historical reasons. As our source playfully suggests, considering the botanist Michael Zwint actually invented chromatography, maybe it would have been a whole lot more accurate to call this unit of measurement a tswet instead of a plate.
All right, let's look at part three, the math of migration.
Now, what's really interesting here is how we make this model functional in a real laboratory setting. To do that, we have to transition from a fun conceptual analogy into rigorous recursive mathematics. Just picture a theoretical cylinder representing our plates, changing over time. At a given time, let's call it I, a specific plate J contains a total mass of analyte. This total mass is essentially the sum of two things. It's the mass carried over by the mobile phase from the previous plate, plus the mass already present in the stationary phase of the current plate from the previous time step. The formula for this is simply the total mass equals the mass in the mobile phase plus the mass in the stationary phase, and the model recalculates this over and over, frame by frame.
If we break that calculation down into a repeating elementary cycle, it looks a bit like this. Step 1. The analyte mass is carried by the mobile phase to a new theoretical plate. Step 2. Adsorption occurs and the concentration re-equilibrates between the mobile and stationary phases. Then step 3. Desorption happens, and the mobile phase progresses to the next plate to start the entire cycle all over again.
Next up is part four, simulating the separation.
So, formulas are great and all, but seeing is definitely believing. Let's move from those abstract mathematical steps to visualizing the actual real-world result of these successive stop-motion equilibria. Think of a computer simulation generated using that exact recursive mathematical model we just went over. It tracks the elution of two different compounds, let's just call them A and B, flowing through a column configured with 30 theoretical plates. When you look at the composition of the mixture at the outlet of the column after the first 100 equilibria steps, you'll notice something amazing.
Those discrete blocky calculations start to form distinct, recognizable peaks, physically separating compound A from compound B. And this brilliantly illustrates the real magic of the model. If you look closely at those initial simulated peaks, they're a bit non-symmetrical and chunky, right? But as you crank up the number of equilibria to a very large number and factor in natural diffusion, those non-symmetrical steps smooth out perfectly. They eventually create the smooth, beautiful, symmetrical Gaussian distribution curves that chemists see in real-world chromatograms every single day.
That brings us to part 5, thermodynamics and equilibria.
To truly understand why compounds separate into those beautiful curves, we have to elevate our discussion a bit to the underlying laws of physics that govern every single plate. Because during each step of our cartoon-like sequence, it's not just one isolated reaction happening. There are at least 3 distinct equilibria balancing out simultaneously within the column. You've got the equilibrium between the analyte and the mobile phase, the analyte and the stationary phase, and the mobile phase and the stationary phase themselves.
So we can actually apply classical thermodynamics to these distributions. The equilibrium constant, K, defines the concentration of the analyte in the stationary phase divided by the concentration in the mobile phase. Now, because we can determine K from real experiments, if we happen to know the temperature, we can use it to determine the variation of the standard free energy. That's delta G0. It's a calculation that proves these imaginary, stop-motion steps are deeply rooted in the universal laws of thermodynamics.
And finally, part 6, legacy of an obsolete model. We've built this model all the way up from a simple cartoon analogy to complex thermodynamic equations. So let's bring this explainer home by assessing its true value in modern science. The source text explicitly calls this model obsolete, but why? Well, primarily because its major limitation is that it fundamentally fails to account for the dispersion in the column caused by the actual physical diffusion of compounds. However, its utility is absolutely undeniable. It leads to definitions and mathematical relations that are entirely universal and are still employed in labs around the world right now. Its real brilliance lies in how perfectly it conceptually simplifies a chaotic dynamic process so that we can actually measure and understand it.
Which leaves us with a genuinely fascinating final thought to ponder. Think about it. The theoretical plate model relies on physical structures that do not exist, and it totally ignores key physical realities like diffusion. Yet, it works incredibly well. It really makes you wonder, does a scientific model actually need to be physically real, or does it just need to be mathematically elegant enough to reliably predict the truth? Thanks so much for joining me for this explainer, and keep questioning the science behind the scenes.